we have a situation where we have a bottle sealed, except that we have a thin tube down here into some water. And we heat this system up to the point where water rises to some given height, h. So h would be the distance from here to here. By Bernoulli's equation, the pressure here differs from the pressure here. Let's call this point A, call this point B, and B is inside here, okay? Down here where the shark is on the surface of the water, okay? I mean, water's always got sharks in it. We understand this, don't we?
Yeah, that's all right.
Okay? So there's small sharks in a small flask, big sharks in a big flask. You gotta watch out for them, okay? Ones come out of the water fountain aren't big enough to hurt you. So you just drink more protein. Okay.
It's all about protein.
Now, Bernoulli.
Yeah, buddy.
Y sub A equals Y sub B plus H. In other words, it's obvious, right? And B sub A and B sub B are both essentially zero, unless the shark is very agitated. Okay? And that really wouldn't make a difference. So, actually could, if the shark is near this point. Okay, B sub A, though, is approximately to B sub B, which is zero. So, delta P is easily found. Now, this is an open tube. So the pressure here equals atmospheric pressure at the open end, and the tube is open from here to here, so it's also equal to this. Using a couple symbols, we can say delta P AB. Change the pressure from A to B. Okay? Where's the pressure going to be greater, at A or at B?
B.
Why? Because at B, you have to have enough extra pressure to support this column of water, right? Okay? So we can easily calculate those. We give them the height. It's really all you need. So we can easily find the pressure here. Now, air volume is A, V. Okay? And we'll call that V naught. Okay?
Whenever I did everything, I was doing it right.
This is sealed, no air can get in or out. Okay? Temperature, T naught. Now we assume this is a rigid container. It doesn't expand at least or contract due to pressure or due to temperature changes by a significant amount. In other words, any expansion or contraction, and any change in volume due to expansion or contraction here is much less than the original volume. So we're going to just assume the volume is constant. Okay, so we have the pressure here. If you give them the height H, you can find the pressure at B, right? Original pressure atmospheric. That's before you start raising the water. Okay? So if this thing starts out at atmospheric pressure, what do we have to do to raise the water up to here? We don't get to change the volume of the air. We got to increase the pressure in a closed container. How do we do that?
Heat it up.
Heat it up. Okay? So, PV equals nRT. N and V are constant, so P over T equals NR over V is constant. Okay? If P1 equals PB, now we're going to call that P1, and we have P naught equal to atmospheric pressure. Then we have this. So T1 is T naught times P1 over P naught. Okay? So we can figure out at what temperature we'll have water at this point. Make sense? Okay, that's a good start.